Hello everyone, welcome back to my channel. This is Nipa Patel from the Math Masters, and today we are going to cover next few questions of exercise 1.2 of chapter 1, Relations and Functions. Please remember to like the video and subscribe to get the notifications for the new and upcoming videos. Let's begin.
Question 3. Prove that the greatest integer function f r to r given by f of x equals greatest integer x is neither 1 1 nor onto, where greatest integer x denotes the greatest integer less than or equal to x. So what is the meaning of this symbol? That means greatest integer which is less than that number or equal to that number. But it must be an integer. Okay, so let's first learn about how this function is going to look like. So f of x equals this function. This is called greatest integer function. So if I plug in 1 in here, so greatest integer of 1 is 1. If I plug in negative 3 in there, then greatest integer of negative 3 is going to be negative 3. If I plug in 0, yeah, it is going to be 0 because it is an integer, so it is going to be equal to that integer. So the answer is going to be 0 for that. Now let's try plugging in few decimals. So if we plug in 0.4, then greatest integer of 1.4, then greatest integer of 1.4 is going to be 1. What did they say? This denotes the greatest integer less than or equal to x. So less than or equal to 1.4. 1.4 is not an integer. So greatest possible integer which is less than this is 1. Let's say if I plug in f of 2.1. So greatest integer of 2.1 is going to be 2. Let's plug in few of the negative decimals. Negative 2.5. Then greatest integer of negative 2.5. So don't write negative 2. It must be negative 3. Why? Because less than this integer. If I write negative 2, then it won't be less than negative 2.5. That will be greater than 2.5. We can have greatest integer which is less than this or equal to this. So it must be negative 3. Let's do one more. Let's say f of negative 1.7. So greatest integer of negative 1.7 is going to be what? Negative 2. We cannot write negative 1. Why? Because it must be less than negative 1.7, which negative 2 is. Okay, so I think now you have idea that greatest integer function means what. So it's this. It's going to work this way. Now we are given what? That relation is from R to R, real number to real number. So let me make that here. So real number, this is also real number. Let's say this is domain and this is our codomain. Now function f of x goes from here to here, and that function is greatest integer function, and that we denote this way. Now let me write bunch of values in here. There are like all real numbers are in here in this domain. Let me write negative 4, negative 2, 0, 1.3, 1.6, then 1.8, then 2, and then many more. Here also maybe similar to this. Let me write negative 4, negative 2, 0, 1, 2, 3, 3.3, keeps on going. I'm just picking few numbers. Otherwise, in this domain, in this codomain, you have every real number that you can think of. Okay, so now let's establish the relation from one to other, from domain to codomain. Now, if we are going to look for the greatest integer for negative 4, it's going to become negative 4 because negative 4 itself an integer, so less than or equal to that number. So negative 4 is going to get connected to negative 4. Negative 2 is going to get connected to negative 2. 0 is going to get connected to 0. Now 1.3 is going to connected to 1. 1.6 is also going to connected to 1. Right? 1.8 is also going to connect to 1. These all are going to connect to 1. So looks like this is not 1 1, definitely not 1 1. Why? Because 1.3, 1.6, 1.8, few more, like not just few, like million more are going to get connected to 1. So f is definitely not 1 1. And when we know that function is not 1 1, we don't need to prove it, we just need to show the counter example. So let's say 1.3 and 1.4 or 1.6, because we can see 1.6 here. So 1.3 and 1.6, they both belongs to domain R, and f of 1.3. So when you find greatest integer of 1.3, you are going to get 1, and f of 1.6. So if you find greatest integer for 1.6, you are going to get 1. So we can see from here and here that f of 1.3 is equal to f of 1.6. They both are same, even though 1.3 is not equal to 1.6. And since 1.3 and 1.6 are different numbers and still they both have the same output, means the function f is not 1 1. That means the function f is not injective, but we don't need to use that word for now. So yeah, f is not 1 1, and the reason is that because we can find the counter example in here. Right, now we are going to check for onto function. Now onto means what? That every element of this codomain must have some pre-image in this domain. Now this 3.3, if we look for this pre-image of 3.3. So 3.3 is a greatest integer for which number? 3.3 is not even an integer. So of course 3.3 will not have a pre-image in this domain. So we can say for onto. So it is not onto either. Why? Because there are decimals in the codomain which are going to be free. They are not going to get connected to anything in this domain. So they are going to be spare elements in our codomain, and when you have spare elements in codomain means that function is not onto function. Okay, so 3.3 belongs to codomain R, but 3.3 has no pre-image, has no pre-image in domain R. So f is not onto. So the function f is not onto. We had to prove that this greatest integer function is neither one, it's neither 1 1 nor onto. We just did that. F is not 1 1, f is not onto, hence proved. So we can just write what? Hence proved. Question 4. Show that the modulus function f r to r given by f of x equals mode of x is neither 1 1 nor onto, where mode of x is x if x is positive or 0, and mode of x is negative x if x is negative. So what function you are given from r to r, and that function is f of x equals mode of x. Now this function is actually a piecewise function. So it is x when your x is greater than or equal to 0, and it is going to be negative x when your x is less than 0. So this function is actually this piecewise function, and that's what they tried to tell you in this other part of the sentence, that where mode of x is x if x is positive or 0. When x is greater than or equal to 0, it is x, and it's negative x when x is negative. So it's negative x when x is less than 0, right? Okay, now the function is from real number to real number, real number to real number. So R to R. So this is our domain and this is our codomain. Now all the real numbers that you can think of, they are all in here in this domain and they are all in here in this codomain as well. Now let's think of that lots of number from negative infinity. Let's negative 3, then maybe let's use decimal as well, then 0, then 1, then 2, then 3, 3.5, 4, and then bunch of more, right? Similar here. Let's use negative 3, negative 1, then 0, then 1, then 2, then or let me use 1.5 as well, then 2, then 3, then 3.5, then 4, then keeps on going. It's not that they have just this many values, huh? I think you got that. All the real numbers that you can think of. I was just trying to think that what I'm going to do now in few minutes. That's why I was just picking few numbers from those numbers that are going to make more sense for us, that why it is neither 1 1 or nor onto. Okay, so function that you are given is f of x from this r to this r, and that f of x is mod of x. That f of x is, and f of x is mod of x. Now, if you find that mod of negative 3, mod of negative 3 is going to be what? That means absolute value of negative 3 is going to be from 3 to positive 3, because we know if you plug in negative 3 in here, then mod of negative 3 is going to be positive 3. So this negative 3 is going to get connected to 3. Now negative 1.5, that's going to get connected to positive 1.5, because the function of mode is what? It converts the negative value into positive value. If you already have a positive value, then as it is. So 0 is going to get connected to 0, then 1 to 1, then 2 to 2, then 3 to 3. So your negative 3 was also connected to 3. Your positive 3 is also connected to 3. So this is definitely not 1 1 function, right? This is definitely not 1 1. And as soon as we find the counter example, we just need to write that counter example to show that that function is not 1 1. So we are going to say what? Negative 3 and 3, they both belongs to domain R, and f of negative 3 is going to be mod of negative 3, and that's going to be positive 3, and f of 3 is going to be mod of 3, and that is also going to be f of 3. Now from this two we can see that f of negative 3 is equal to f of 3, but negative 3 is not equal to 3. But negative 3, this input is not equal to this input, still we got same output. So when this happens, that when two different input get the same get the same output, then that function is not 1 1 function. So f is not 1 1. Now we are going to look for onto function. Now whether this is onto or not, so who is going to decide that? You just need to look at the codomain and try to see, is every number in this codomain connected to some number in domain? That means every number in this codomain, do they have pre-image in this domain? So negative 3, which number's mode is going to be negative 3? None. Why? Because as soon as you use mode, it's going to convert into positive number. So all this bunch of values, all these numbers that are negative, definitely they are not connected to any pre-image in this domain. So this function is definitely not onto. So we are going to write that here for that onto function. And since we know that it is not onto, we just need to show the counter example. When it was onto, then we had to prove it, but this is not onto. That means we need to just show the counter example. So we are just going to show what? That negative 3 belongs to codomain R, but -3 has no pre-image in domain R, so R is, sorry, not R, so F is not onto. That's what we were supposed to prove. Show that this function is neither 1, 1 nor onto. So we showed f is not 1, 1 and we just proved that f is not onto either. So we are just going to write hence proved. Question 5. Show that the signum function f r to r given by f of x equals 1 when x is greater than 0, f of x equals 0 when x is equal to 0, and f of x equals -1 when x is less than 0 is neither 1, 1 nor onto. This is what we are supposed to show. Now we are given this function and we are given from R to R, from real number to real number. So let's make a domain and a codomain, and this is real number set. This is also real number set. Let's say domain here, codomain here. This is function f, and this function f is a signum function. Now we are given the definition of that function already, so we don't need to worry about what is that function, what kind of output it will have. We are given the definition in detail, so that's good. Now in this real number set, in this domain and in this codomain, any real number that you can think of, they all are in here. For example, -4, then -3.5, decimals, fractions, everything, negative, positive, 0, then 1, then even radicals, because irrational numbers are also real numbers. So rational, irrational, everything that you can think of. 3 and infinitely more. Similar here, that again, let me write similar numbers: -4, -3.5, -1, 0, then 1, then 2, then square root 8, then 9, 10, and bunch of more. So every real number is in this domain and every real number is in this codomain. Now if we try to make relation from this domain entries to the codomain entries, let's see how it's going to look like. So if you have -4 as your x, now -4 is what? Less than 0, right? See, when we think of this input, this x value, if your x is -4, that means it's going to come under this. When x is less than 0, it is -1. So -4 is going to get connected to -1. Now -3.5, again that is less than 0. So that is also going to get connected to -1. -2, again less than 0, so that is also going to get connected to -1. -1.7, again going to get connected to -1. Now 0. If your x is 0, then output is 0. So 0 is going to get connected to 0. 1. So 1 is greater than 0. So 1 must get connected to 1. Square root 2, that is also greater than 0. So that is also going to get connected to 1. 3 also greater than 0. So that is also going to connect it to 1. So definitely we can see that infinitely many numbers are connected to -1 and infinitely many numbers are connected to +1. So this is definitely not 1, 1 function. And when we know the function is not 1, 1, we just need to show the counter example. So we are going to show, let's show this, that 1, 3 belongs to real number R, or let me write domain R, belongs to domain R, and f of 1. So if you plug in 1, f of 1, when x is 1 means x is greater than 0, so your output is going to be 1. And for f of 3, If your input is 3, if your x value is 3, that means again x is greater than 0, so that output is also going to be 1. And we can literally see that f of 1 is equal to f of 3. Why? Because both output are exactly same. But this input are not same, but 1 does not equal to 3. And even though the input were not same, still output was same. So this function is not 1, 1. Therefore, f is not 1, 1. What we had to show, that we need to show that this given function is neither 1, 1 nor onto. So one of the part we finished, that this is not 1, 1. Now we need to look into onto function. Now, if all the elements in your codomain are occupied with some pre-image in domain, then it is onto. Now you can literally see that every number from domain, it is connected to just 3 of the numbers, -1, 0 and 1. Every other number is free. So you can find millions, you can find infinitely more numbers, infinitely many examples in this codomain that does not have a pre-image in this domain. So pick any of them and state that it is not onto. So we are going to say what? Okay, 2 belongs to codomain R, but 2 has no pre-image in domain R, therefore f is not onto, right? Because there is no number from domain that is connected to that 2. You could have written -4, you could have written square root 8, you could have written 10, any example. Just you need to pick one counter example is enough to prove that that function is not onto, or that function is not 1, 1, which we just did. So question done, or you can even write that hence proved. Question 6. Let A equals this set and B equals this set, and let f is equal to 1, 4, 2, 5, 3, 6 be a function from A to B. So they are talking about a function from A to B. That means in a diagram, if we want to visualize, then the domain is A and codomain is B, because you are given function goes from A to B. Now we need to show that this function f is 1, 1. Now what are you given? You are given that A is equal to 1, 2 and 3, and B has elements 4, 5, 6, 7 in it. So if I just list them here, 4, 5, 6, 7, then look here, see, your f is what? This. So your f is given as 1, 4, 2, 5 and 3, 6. This means what? 1 is connected to 4. That means 1 is connected to 4. 2, 5 means 2 is connected to 5. And 3, 6 means 3 is connected to 6 in this codomain. Now we were given that relation already, and we made that path in this diagram. Now by the look of it, can you say that every input or every element in this domain is connected to some distinct output, some distinct element in this codomain? Yes, because 1 goes to 4 only, 2 goes to 5 only, 3 goes to 6 only. So this is clear cut case of f is 1, 1. Clear cut case of f is 1, 1. Now they didn't ask that that function is onto or not, but just to see that this function is onto or not. So this function is not onto. Why? Because this 7 is free. This 7 is not connected to any pre-image in this domain, so it is not onto. But we were not asked that, so let's not worry about that for now. Whatever we were given, we used everything. Now we just need to show that this function is 1, 1, which we actually have, but just show it. So like let's in standard method, we are going to take two different elements from input from this domain. So let's say this both belongs to, domain is A, so belongs to A. And that means we always start with what? Make the output of those elements exactly same as each other. And if we think that x1 was 1 and x2 was 2, then if that output is same, see, it did not happen. This output was different, this output was different. So both output are going to be same only when your x1 is equal to x2, when your both values are actually exactly the same. Or in other words, if you are talking about the same element, this only happens when these both are same, then and then you get the same output. That means this function is 1 1. So f is 1 1. Question 7. In each of the following cases, state whether the function is 1 1, onto, or bijective. What was bijective? Bijective means if a function is both 1 1 and onto, then that function is called bijective function. Now we are going to start this question 1 in this. Now in this question 1, you are given that function goes from real number set to real number set, means domain is real number and codomain is also real number. And function definition you are given is f of x is equal to 3 minus 4x. Now first we are going to see that whether the function is 1 1 or not. So to do that, we are going to pick two elements from domain. Our domain is real number set. So let x1, x2, those two different input, two different elements we are taking from our domain R. This R is our domain. We are talking about domain here. So let's pick two elements from that domain. Here we are picking x1, x2. Now from that function definition, f of x is 3 minus 4x. So f of x1 is going to be what? 3 minus 4x1, and f of x2 is going to be 3 minus 4x2. Now to prove 1 1, we start with f of x1 is equal to f of x2. Now if these two are same, that means this 3 minus 4x1 must be equal to 3 minus 4x2. So let's write that down. 3 minus 4x1 equals 3 minus 4x2. Now if it is 3 minus 4x1 equals 3 minus 4x2, 3 and 3 can cancel out. So then you will have negative 4x1 equals negative 4x2. Again, negative 4 and negative 4 can cancel out. So you actually got what? x1 equals x2. So this happens that you get same output for two inputs, but when those two inputs are exactly same. So that means it says that two outputs are going to be same only when you are talking about the same element from that domain. So of course, from this result, we can conclude that f is 1 1. Now we are going to show onto. Now for onto, we need to pick one element from our codomain. So from our codomain, we are going to pick okay, we always pick that, our output as y. So let y belongs to R. In this case, I'm talking about codomain. Why? Because in onto we always start from one element from the codomain and we try to find the pre-image for that in the domain. Because as soon as we prove that, then that function is onto. So let's pick one element from that codomain. Here we picked y, and since y is in the codomain, that means y is the output, and function definition is what? F of x equals 3 minus 4x. So that is actually what? That if you have a domain here which is R and you have a codomain here which is also R, and your function is what? Your f of x is equal to 3 minus 4x. So if you pick a value from here and let's call it y, then there must be a pre-image called 3 minus 4x somewhere here. right? Or I shouldn't say that, there must be some x in here, which is what, 3 minus 4x equals y, right? Why? Because this is what 3 minus 4s, that's the function definition. So let y belongs to R in codomain, and now we are going to try to find the pre-image. But y is nothing but the element in codomain. That means y, you are going to get y as what, using this function definition. If you pick some value x, and if you multiply by 4, and then if you subtract that value from 3, that must be your output. That's what our function says. So if you pick an element from this codomain, that codomain y equals that definition that you are given, 3 minus 4x. Now try to solve this for x. So if I try to solve this for x, then this is going to be, I am going to send 4x over there, send y over here. So 4x is going to be 3 minus y, and then x is going to be 3 minus y over x. Sorry, 3 minus y over 4. Now if you look here, is this going to belong to the domain R? Of course, right? Because y is some real number, and then if you subtract 3 minus that real number and divide by 4, of course it's going to belong to the real number set in your domain. And as soon as you have that pre-image in domain, that means, yeah, it is actually onto function. Why? Because you picked a element from the codomain, and you now found that there is some pre-image in this domain, right? We can show further by showing that now f of x, what was the function definition? F of x equals 3 minus 4x, right? F of x equals 3 minus 4x, and this value of x you can plug in, this value of x you can plug in this x. So to do that, I just need to plug in this x value, which is 3 minus y over 4. Now simplify this, 4 and 4 is going to cancel out. So you are going to end up getting 3. Now 4 and 4 has cancelled out. So minus 3 and minus times minus, so positive. So 3 minus 3 plus y, and that means you actually got what? F of x equals y. As soon as we get f of x equals y, that means we can conclude that your function is onto. So f is onto. And see, our function was 1 1 as well, our function is onto as well. So you can just conclude, hence f is bijective, because a function is bijective only when that function is 1 1 and when that function is onto. Now part 2 of this function. Here again you need to show whether the function is 1 1, onto, or bijective. And this time you are given function from R to R, and function definition you are given as f of x equals 1 plus x square. Now from real number to real number. So from domain to this codomain, let's call this domain. Let's call this codomain. Now all the real numbers that you can think of, they all are in here in this domain and in this codomain, but let's write few. So negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and keeps on going, right? That 3 was not quite visible. So 2, then 3, and it keeps on going. Same way here in this real number set, again you will be able to see, let's say negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, and keeps on going, because it's all the real numbers that you can think of. All rational, irrational, that means all decimals, fractions, square root, cube root, whatever you can think of, all real numbers are there in this domain and in this codomain. Now you are given a function from this R to this R as f of x equals 1 plus x square. As f of x equals 1 plus x square. Now, since the function definition is given, which is 1 plus x square, let's see that this negative 4 is going to get connected to what number? We don't have that here. So, okay, let's look at negative 2 because I had a limited space, so I couldn't write all the real numbers, of course, right? So, negative 2. If you plug in negative 2 in here, so 1 plus negative 2 square. So, negative 2 square is going to be 4 and then plus 1. So, negative 2 is going to get connected to 5, right? Why? Because if you plug in negative 2 in here, that means you are doing 1 plus negative 2 square. Negative 2 square is 4, 4 plus 1 is 5, so negative 2 is going to get connected to 5. Same way, if you check for 2, so if you do f of 2, if you find f of 2 value, then you are plugging in wherever you see x, you are plugging in 2. So 2 square 4, 4 plus 1 5. So for 2 as well, you are going to get 5. As soon as we see this 2 happening, that means we can say that it is definitely not 1 1 function. Why? Because negative 2 and 2, they both are connected to the same value in the codomain, right? So I don't need to even connect anything else. I can just start writing 1 1, and since it is not 1 1, we just need to show the counter example. So negative 2 comma 2, this both belongs to domain R. Then we know f of negative 2 is going to be what? 1 plus negative 2 square, which is going to be 5, and f of 2 is going to be 1 plus 2 square, that is also going to be 5. Now we can see that f of negative 2 is equal to f of 2, but negative 2 does not equal to 2, so f is not 1 1. So f is not 1 1. Okay, so now we need to show for onto. Now onto. Now a function is going to be onto when all the numbers in this codomain are occupied by this domain, or all the numbers in this codomain has pre-image in the domain. So see 1 plus x square. So negative numbers are definitely not going to get connected to any of the domain numbers. Why? Because if you do square of some number, even though you plug in negative number, even though you plug in decimal, even though you plug in fraction, even anything, but as soon as you do square of it, that number is going to be positive, and now you are adding 1 to that. So definitely it will never be a negative number. So you cannot find a pre-image of negative 4, negative 3, negative 2, negative 3.7. None of those negative numbers you won't be able to find a pre-image. And that does not mean that only negative numbers. There are few numbers, not few, there are infinitely many numbers in this positive side of the real number as well, that they don't have a pre-image in this domain. But we just need to show one counter example. If that example shows that it is not onto, then the function is not onto. We just need to find one counter example. So we are just going to go with that negative 1. So negative 1 belongs to codomain R, but negative 1 has no pre-image in domain R, so f is not onto, right? Think this way, 1 plus x square equals negative 1 is it's never going to happen. Why? Because as soon as you think of that, that 1 plus x square equals negative 1, we are trying to find some pre-image of negative 1 in this domain. So that means negative 1 must be equal to some input square plus 1. So that means x square is equal to negative 2. See, square of some number is never going to be negative. So we will never be able to find pre-image of this negative 1. And since we got that counter example, we are safe to say that that function is not onto. Now that function, this second question, the function in this second question is not 1 1. That function is not onto. So you can say hence function f is not bijective, because we were supposed to talk about bijective as well, right? Okay, then we are done. Question 8. Let A and B be sets. Show that function f A cross B to B cross A such that f of A comma B is equal to B comma A. So this function does what? If you enter A comma B, it flips it and it makes it B comma A, is bijective function. Now let's try to understand this question with some example. So what you are given? You are given a function from set A cross B to set B cross A. Now we know A cross B means in A cross B, you will always have as first coordinate as the coordinate of A set, and second coordinate is going to be the coordinate from B set. And this function definition, the function does what? That if you enter AB, that becomes B comma A. That comes out as B comma A. Now let's look at some example. Now in this we are going to let A is equal to, let's assume 2. I am taking just 2 so that I don't end up making A cross B as my tiring work. So A equals A comma B, and let B equals 3 comma 4. Okay, now if we find A cross B, A cross B will have what elements? See, our domain is A cross B, so A cross B is going to have 1 comma 3, 1 comma 4. Why? Because this element with both of this, and then I'm going to take this element with both of them, and then I will have all the possible elements of A cross B. Now let's try to build B cross A. Now in B cross A, we are going to take first element from B and second element from A. So let's take 3. 3 is going to go with 1 as well. 3 is going to go with 2 as well. And now it's 4, and again it's going to go with 1 as well. It's going to go with 2 as well. So this is our B cross A. Now if I try to show that with that diagram of domain and codomain, so this is our A cross B, our domain, and this is our B cross A. This was our domain, this was our codomain. So I wrote this way. Now function f goes from domain to codomain, and let's now list all these elements in here and in here. So A cross B elements we are going to list here: 1 comma 3, 1 4, 2 3, 2 4, and these elements I am going to write here: 3 1, 3 2, 4 1, and 4 2. Now function definition is what, or what does this function machine do? That if you enter AB, if the input is A comma B, the output comes out as B comma A. So 1 3, it's going to get connected with 3 1. Why? Because if you enter 1 3, it should be flipped. So 3 1. Now 1 4, so that's going to be 4 1. 2 3, so it's going to get flipped. So 3 2, and 2 4, so it's going to get flipped and going to become 4 2. So see, from this diagram we can literally see that 1 to 1, the function is 1 1. So we can say that function is 1 1 because every input has distinct output. So yeah, it is 1 1, and it's onto as well. Look at this B cross A, look at this codomain. Every element in this codomain is occupied with some pre-image from the domain, so it's onto as well. So we have done this with example. Now we are going to try to prove that why it is 1 1 and onto without an example. So that another method is going to be, let's try to prove 1 1. This was just my way of showing you that what do they mean by this A cross B to B cross A, and then function AB equals B comma A. So this was the whole idea what that function is. Now to prove 1 1, let A1, B1, and A2, B2 belongs to this A cross B. Okay, because we have to generalize that element. Why? Because we are trying to prove it, because they both functions are 1 1 and onto. So when we have to prove it, we don't use example, but we just show by picking two elements from the domain, and then by making their output same, we are just going to derive that actually those output are going to be same only when these both elements are exactly same, right? So that is our method, that how we prove that the given function is 1 1. So for now we are letting that there are two different elements in A cross B. One is A1 B1 and other is A2 B2. Now function says what? We are given function A comma B is equal to B comma A. So that means f of A1 B1, if we do, so now f of A1 B1, we are going to make it equal to f of A2 B2. What do we always do? We take two inputs or two elements from the domain, and then we start with making their output same. And here we took these two elements in our domain, and I am making their output same by entering them into the function machine. This is our function machine, f of AB. So if I do f of A1 B1, then it's going to give me the output for f of A1 B1. And if I'm going to look at the output of f of A2 B2, it's going to give me f of A2 B2. So now I'm just comparing, as we always do, the output of these two different elements in this domain. Now function machine says what? That if you have AB, it becomes BA. So f of A1 comma B1, it's going to become what? B1 comma A1 is going to get flipped, right? And this is going to become B2 comma A2. Now when two coordinate pair, if you are given exactly like this, that means what? B1 is actually B2. B1 and B2 has actually no difference. Why? Because you got equal to in between. So that means A1 is equal to A2, B1 is equal to B2. So if I flip it, it's still going to be same. A1, B1, and if I make it A2, B2, still yeah, same. A1 is equal to A2. See, here also it was A1 equals A2. Here also A1 equals A2. Here it was B1 equals B2. Same, B1 equals B2. So yeah, I am allowed to do that. I can flip it. And if I flip it, those both are the exactly same elements that we started with, and we thought they both were different, but they are not. So when the output is same, that means you are talking about the same element. And as soon as we prove this, that means we have proved that f is 1 1. So f is 1 1. Now we need to prove onto. Now for onto, we need to take one element from this codomain, and we need to try to find a pre-image in this domain, right? Okay, so we are going to take some output from this, that means some value from our codomain. Let's call it B comma A, because that's what they have given us, right? That output becomes BA, so I'm just taking that only. So let B comma A belongs to B cross A. That means in this codomain. Now we need to find some pre-image for this B comma A in this function. Now since we know that it's going to get flipped, right? So if it's going to get flipped, and if we think this way, that whose output is going to be B comma A, right? We know what that function machine does, that if you enter AB, it's going to come out as BA. So right now we are thinking that if the output is BA, then what could we have entered in the function machine? We must have entered A comma B, because the function does what? It flips it. So that must be A comma B that we have entered, or that must be the pre-image A comma B, where this B comma A is connected. And see, we got the same function definition that was given in the question. So f is onto, and hence since it is onto as well, since it is 1 1 as well, hence F is bijective. Okay, so first we understood this given situation with the example. Yeah, that was straightforward. This was, I think, way easier. If you would like in this kind of question, I think that's fine if you show it with the example. But since we always know that when we are supposed to prove that the function is 1 1 and onto, we always use this generalized method, kind of the way of how we prove it. And we always do what? We take two inputs or two elements from the domain, and then we find the function value, and we make that function value equal to each other. And if that happens only when those two inputs are actually exactly the same, then the function is 1 1. And in onto we do what? We take one element from codomain and we think of the pre-image of that. And if that pre-image exists for that element, that means for every element in that codomain there must be a pre-image in the domain. And if that is true, then yeah, that function is onto. And if it is 1 1 and onto both, then the function is bijective.
Okay, so that's it for this video. Please remember to like and subscribe. See you all in the next video. Thank you.